Hello everyone, a warm welcome to my presentation. My name is Ananya A. I am a fourth year student from Electrical and Electronics Engineering Electrical Department at GMIT College. Today I am incredibly excited to present my final internship project submission, an IoT-based home automation system. This project is a culmination of my work during the Emertxe Internship program developed during the invaluable guidance of the mentors. As a student of electrical engineering, the intersection of hardware, firmware, and cloud networking has always fascinated me. Over the course of this presentation, I am going to walk you through how I designed, simulated, programmed, and implemented a smart home ecosystem that bridges microcontrollers with modern cloud computing. Let us look at the core abstract and motivation behind this development. Modern home faces a silent challenge: immense energy wastage due to manually controlled appliances, left active when unnecessary. To solve this problem, my objective was to design a system that automates, controlled based on real time ambient conditions, while still giving users the agency to override these decisions from anywhere in the world. To do this, I established four primary objectives: to engineer a reliable remote control mechanism for high voltage AC appliances using relay logic. Second one, and to implement autonomous local decision making, such as turning on light fixtures using a photoresistor, which means LDR, when natural light fades. Third one, to monitor ambient temperatures using a highly calibrated analog sensor and automate climate control using a simulated fan. Fourth one, to integrate a cloud interface using the Blink IoT platform, allowing a real-time monitoring and control on a smartphone. To understand how these components interact, let us look at the smart block diagram. So the system can be conceptually divided into three clear architectural layers, which is inputs, processing, and outputs. On the input side, we have our physical environment monitors. We have the LM35 analog centigrade temperature sensor and the LTR, which means light dependent resistor. These sensors continuously generate analog voltages that represent environmental parameters. These analog signals are routed to the analog pins of our processing unit. The processing unit is the heart of our system. The Arduino Uno, driven by the AT 328T microcontroller. The Arduino processes these incoming analog signals, runs our embedded firmware logic, and translates them into physical decisions. These decisions are reflected through our output devices. We have an I2C, which is 16 cross 2 LCD display for local output, showing current sensor statuses directly on the board. For the physical automation of appliances, Arduino controls two mechanical switches via relay module. So the relay 1 will used as lighting load, which is represented as a lamp, and relay 2, which is used for cooling the load, which is represented as a brushless fan. So finally, we have the communication bridge. The Arduino communicates with the ESP8266 Wi-Fi module over a serial UART interface using 80 commands. The ESP8266 connects to the local access point and synchronizes our variables, with the Blink cloud. The cloud then reflects this data onto the custom smartphone dashboard, completing a full closed loop IoT system. Now, let us examine the specific hardware choices that make this architecture robust, reliable. So, first, Arduino Uno. The first one, Arduino Uno R3. As an electrical student, I choose this board because it operates on a standard 5-volt system, offers a clock speed of 16 megahertz, and features 6 analog input pins paired with an onboard 10-bit analog to digital converter, which means ADC. This is ideal for precision reading of analog sensors. Second, our ambient temperature monitor is the LM35 sensor. Unlike the thermistors, which are highly nonlinear, the LM35 is a precision integrated circuit temperature sensor whose output voltage is linearly proportional to the Celsius temperature. It operates at a scale factor of some value, which is meaning to it produces 10 millivolts for every single degree Celsius, spanning a range from minus 55 degrees Celsius to plus 150 degrees Celsius. For the light detection, we implement a light dependent resistor or LDR arranged in a voltage divider configuration with a static resistor as light falls on the LDR. Its internal resistance drops drastically from mega ohms down to few hundred ohms, resulting in changing a voltage profile on analog pin A1. For our output actuators, we use relay modules. Relay are electromechanical switches that isolate our low voltage DC microcontroller circuit from high voltage AC loads. This ensures completely safety for the microcontroller during the physical appliance operations. Moving to our software stack, which handles everything from design to the final execution. For development, I wrote the firmware within the Arduino IDE using embedded C. The environment allows us to compile our logical constructs down to machine readable hex files, which means hexa files. To simulate our design before deploying the physical hardware, I used Proteus VSM in electrical engineering. Physical prototyping without circuit validation can lead to component damage. So Proteus allowed me to map out the entire schematic, verify the logic, and debug the hardware issues in the real time. On the networks, the cloud is driven by the Blink IoT. It provides an advanced, stable MQTT-based cloud broker that allows me to link the microcontroller parameters with the virtual pins. To make the interface user-friendly, I built a custom mobile application on Blink featuring interactive which analog gauges for temperatures, a bar slider for light intensity, the custom toggle switches for manual device control. Let us look at the mathematics and the calibration process running inside the microchip. Because computers only understand binary and the analog voltage values from our sensors, which must be converted into digital data. So the Arduino Uno utilizes 10-bit analog to digital converter. This means it maps incoming analog voltages between 0 volts to 5 volts into discrete digital steps ranging from 0 to 1023. Therefore, each discrete digital step represents of resolution we can be termed as 5 volts with respect to 1024, which gives us 4.88 megavolts. So our resolution can be 4 point approximately 4.88 megavolts. To calibrate our ELM35 temperature sensor, we can apply this basic formula in our firmware. So when voltage is in megavolt, we can use this formula when the numerator is ADC reading into 5000 megavolts with respect to 1024. Since the LM35 produces 10 megavolts per degree Celsius, we calculate the final temperature in degrees using T Celsius formula. We can we know the old formula voltage in megavolts with respect to 10 megavolts, which is equals to ADC reading into 5 into 100 with respect to 1024. In the code, this is executed as a floating point calculation to retain decimal precision. The automation logic itself is straightforward. For lighting, we monitor the LDR reading. If the light percentage drops below 30% and the user has not activated a manual override, the Arduino writes a digital high to pin 4, activating relay 1. Similarly, if the calibrated temperature exceeds 35 degrees Celsius, the controller automatically sets pin 5 to high to activate the cooling fan. No engineering project is without its challenges. During development, I faced three main technical hurdles. So, the first one is calibration accuracy. Initially, raw sensor values from LM35 suffered from analog noise. To solve this, I implemented an averaging filter in my code that samples the pin 10 times consecutively and calculates the mean, delivering a smooth, reliable reading. Second one, network protocol overheads. Managing stable communication over the ESP8266 was a challenge. Sometimes cloud syncs delay led to latency in relay trigger responses. I resolved this by utilizing non-blocking timers instead of using the resistive or restrictive delay function in the Arduino main loop. This kept the system running continuously. Third one, the simulation gap. Connecting a local simulator to a remote live cloud network is difficult. I solved this by configuring virtual serial port on my development computer, allowing the Proteus simulator to send the serial data directly to a local bridge utility that routes packages to the Blink cloud. Welcome to my live simulation workspace. On my screen, you can see three distinct columns. In the center column, we have our Proteus stack circuit schematic. You can see our I2C 16 cross 2 LCD display, the analog slider control simulating our LM35 and the LDR sensors, and our active actuators, the AC lamp connected to the pin 4 and our cooling fan connected to pin 5. Below the schematic, you can see our microcontroller firmware monitor displaying loops in real time. On the right, you can see our Blink mobile interface. This is an accurate emulation of the smartphone dashboard. It displays the live gauges representing a sensor and remote switch bits mapped to virtual pins. So let us go to our first task. Let us first test our automated lighting control. Watch the LDR light sensor slider and our physical lamp. Currently, our LDR is sensing 80% ambient light, which represent a bright, sunny afternoon. Therefore, our simulated lamp remains off and the LCD screen shows light is 80% and auto. Now, I will simulate night falling by dragging the LDR slider down below our programmed 30% threshold. Let it set it to 15%. I think this is auto, right? Yeah. I'm going to take it below 30%. So this is 30%. Yeah. This is 30%. You can see this is 30%. And I'm going to draw this below 30%, which means of 15%. Yeah. Look at what happens instantly. The microcontroller registers this drop. Pin 4 immediately triggers relay 1. Our simulated AC lamp glows yellow, indicating it is active simultaneously on our Blink app, which is here. On the right, the light intensity indicator bar drops, reflecting 15% in the real time. This proves our automation logic is fully operational. Next one. The second task is automated temperature control. Let us demonstrate our automated climate control using the temperature sensor. Currently, our temperature is 30 degree Celsius and our cooling fan is inactive. You can see that the cooling fan is inactive and the pin 5 is written low. Okay. Now let us simulate a hot summer afternoon. I will drag our LM35 temperature sensor slider up. Let's push it towards 35 degrees Celsius threshold and set it to 42 degrees Celsius, which means high temperature. See what happens when I will set it to 35 or more. Yeah, you can see the difference. When I set it to 35 degree, it starts to on. Cooler is on. And when I just increase the temperature to 42 degrees Celsius, observe the system reaction. The moment ADC registers a temperature above 35 degrees Celsius, pin 5 is written high. Our cooling fan instantly begins to spin to cool down the system. If we look at the local LCD display here, it updates to show our high temperature alert. On our Blink dashboard, which is over here, the temperature gauge has instantly turned red and we receive a warning log for critical high temperature detected. This highlights how local microcontrollers can communicate critical alerts to remote cloud clients. And our next task is Blink mobile app manual override demo. So let us demonstrate one of the most powerful features of our system, the manual override. So although ambient light is currently high at 80 degree 80%, meaning the local automation logic wants the lamp off. Let us assume the user want to manually switch on the lamp from their phone, which means here this is auto and I want to make this manual. I will on both of them. See, you can see here it is manual. When I will when I will click on this lamp control, see, lamp control toggle switch on our Blink app. Look, the switch state changes to on. Here, the on. The virtual phone app sends a packet through our simulated cloud. Our local microcontroller immediately catches this override command, sets pin 4 to high, and our physical AC lamp lights up. Here we can see this. So there is any changes here, is there it is of any bright day or a dark day or any dark, there is no changes in the lamp because this is manually controlled. Look at the local LCD screen. Now it displays manual. Here we can see this. Instead of auto mode, this override takes immediate priority over sensor readings, ensuring the user always maintains ultimate control over their smartphone. And the last task is Advanced Gemini AI Copilot Diagnostics. So, to elevate this final presentation, I integrated a cutting edge feature, the Gemini AI Intelligent Diagnostics module. In the real world, industrial installations, maintaining system stability is critical. By connecting a simulated microcontroller to the Gemini API, we can run real time smart analysis. Now I'm going to click the Analyze Status button. Simulator is now compiling our hardware matrices such as temperature, light intensity, and relay states and sending them directly to the Gemini 2.5 flash model. So let us simulate it. Okay. Look at the response on the screen. The AI has instantly analyzed our current system metrics and delivered a custom feedback. This demonstrates how modern IoT grids can utilize edge computing and LLMs to run predictive maintenance and save energy automatically. This brings me to the end of my final project presentation. Developing this IoT home automation system has been a deeply rewarding experience that has bridged my textbook engineering theories with practical, real world systems. I want to express my deepest gratitude to all my mentors for their constant support and to entire MRC team. Thank you so much for your time and for watching my presentation. Thank you.